Hello everyone, I am Shikong Pang from Henan University. Today, I am presenting our paper titled, Motif Consistent Counterfactuals with Adversarial Refinement for Graph-Level Anomaly Detection. First, the goal of our paper is graph-level anomaly detection. Graph-level anomaly detection focuses on identifying anomalies or irregular patterns in entire graphs rather than in individual nodes or edges. This type of analysis is particularly useful in various domains such as social networks, cybersecurity, finance, and biology, where the structure and properties of the whole graph can indicate unusual behavior or events. Next, we address the issue of graph perturbation leading to graph distortion. Most existing studies directly introduce perturbations, for example, flipping edges for data augmentation. However, this easily alters the semantics of the generated examples and affects the graph distribution, leading to suboptimal performance. Additionally, many existing methods generate suboptimal augmented data, limiting their effectiveness in enhancing generalization capacity. Our approach consists of two parts. The first part is the generation of the initial graph. Specifically, this involves selecting a core subgraph from one graph and an environment subgraph from another graph, then combining them into a raw counterfactual graph. The second part is a GAN-based graph optimizer to refine the raw graph. This adversarial training will encourage the generated graphs to conform to the patterns of realistic graphs, that is, meet the requirement of the property realism. Further, to ensure the characteristics of counterfactual data, we designed three loss functions. The first is the motif consistency loss. The purpose of this loss is to ensure that the identification information of the generated graph is consistent with that of the given realistic graph. Since the motif decides the category label, this loss encourages the generated graphs to meet the property validity. The second is the contextual loss. This loss is proposed to force the contextual subgraph to be similar to the realistic contextual one. Both the contextual loss and the motif consistency loss compel the generated contextual subgraph and the motif to approach the realistic ones, which can meet the property proximity. The third is the connection loss. This objective is designed to control the number of edges connecting the motif nodes and the contextual nodes in the generated graph. This loss tries to limit the new connection edges, which can control the property sparsity of the generated graphs. Our experimental results show that our method maintains a leading position compared to existing methods. Thank you for your attention.